So we are coming to an end on the session on algebraic extensions. So what we'll do today is we'll have a couple more definitions and results and problems. So that will be the end of algebraic extension. So let us do our first definition here today. So let E be an extension of F. Just an extension, it is not algebraic extension, just an extension of F. So this may contain elements that are transcendental over F or algebraic over F. We have both. But I am only considering the elements that are algebraic over F. So, and alpha comma beta belongs to E be algebraic over F. This means that the extension containing alpha and beta is algebraic. Over F, meaning every element of this extension are algebraic over F. So that implies alpha plus beta, alpha minus beta, alpha beta, alpha over beta whenever beta is different from 0, are elements of f of alpha beta. Because f of alpha beta is a field, so these are elements. So if these two are elements of this field, then sum, subtraction, multiplication and division when beta is different from 0 are elements of this. So this implies alpha plus beta, comma, alpha minus beta, comma, alpha beta, comma, alpha or beta, beta is different from 0, are algebraic over F. So if you take two elements which are algebraic, then it's sum, difference, product and the division all are algebraic, and that implies the elements in E, alpha is algebraic is a field, and it is an extension of F and a subfield of E. So if you take diagram EF, those elements that are algebraic, if you consider all these algebraic elements and the smallest field containing that, or a smallest collection that contains F, beta, gamma and F is a field. This extension or subfield of E, extension of F, this extension of F or subfield of E is called the closure of F over E. is denoted by F E a bar. So basically it is going to be F is less than or equal to F E bar less than or equal to E. So for an example, Q is a field and R is an extension of Q. Suppose you want to find out the closure of Q over R is going to be A in Q. A is algebraic over Q, or let us make it a bigger one, C, and here, yeah, because C is also an extension of Q, and these are actually called the algebraic number, the collection of algebraic numbers. So the collection of algebraic numbers is a field. So the collection of algebraic numbers is a field. See, the elements in C that are algebraic over Q is called algebraic numbers. So we'll do the second definition, this next definition. A field F is algebraically closed if it has a zero of every polynomial in f of x. See, if you take the collection of algebraic number, the collection of rational numbers, then this is not algebraically closed. I'll write it here. Q is not algebraically closed because x square minus 2 belongs to f of x or q of x, and x square minus 2 does not have a 0 in Q. Same here, R is not algebraically closed because x square plus 1 belongs to R of x and x square plus 1 does not have a 0 in R. But C is algebraically closed. If you take any polynomial in C of x that has a 0 in C. Now we have two terms, algebraic closure and algebraically closed. What is the relation between these two? Every algebraically closed field is algebraic closure. Of the field. No problem at all, because every single polynomial in that field has a 0 there. Okay. Now we'll find out if the other inclusion is possible. So we are going to give you an example which shows that if a field is algebraically closed, field is algebraic closure of some extension, then does not need to be algebraically closed. So we'll take example Q. Q is a subfield of Q of x. Actually, Q of x means not like this, Q of x. There is a difference between this and this. This is actually the ring of polynomials in Q. This is actually the field of quotient of Q of x. So this is always an integral domain, and we are making a, so this is a subfield of Q of x, or Q of x is an extension of Q, because if you consider the map Q to Q of x by Q of A is equal to A is a 1-1 homomorphism. So it's definitely an extension. But the closure of Q, actually Q has got another extension, that is R, that is different, and C. I'm not going to take this route, I'm going to take this one. Here, the closure of Q over Q of x, this is actually the elements from Q that is algebraic over Q. And this is nothing but Q itself. Because root 2 cannot be considered here, because root 2 does not belong here. See this, the Q of x and this is Q. Outside Q and inside Q of x are non-constant polynomial in x, not root 2 or root 3 or anything like that. If you go outside of Q in this extension, what you are going to see is the polynomial, non-constant polynomials. Here are all constant polynomials, and on outside this is non-constant polynomial. So those non-constant polynomials are actually not algebraic over Q. So the only elements in this extension that are algebraic over Q are elements from Q only. So here this is equal to Q. So that means Q is an algebraic closure over Q of x. But we know that Q is not algebraically closed. So there are fields that are algebraic closure of itself, but still they are not algebraically closed. So there is a difference between algebraically closed and algebraic closure. Now let us assume that E is an algebraically closed field. Then let us take a polynomial. Let P of x belongs to E of x. Then, because this is a polynomial here of degree n. So, E is algebraically closed means there exists, this implies there exists an alpha 1. There exists an alpha 1 in E such that P of alpha 1 is equal to 0. And that is the definition of algebraically closed. Because every polynomial has a 0 here. Now, if n is equal to 1, then P of x equal to x minus alpha 1. See, if alpha 1 is a 0 of this polynomial, x minus alpha 1 is a factor of this. But if it is 1, if n is equal to 1, then this is the polynomial. Okay? Otherwise, let alpha 2 okay, otherwise we can write p of x equal to p1 of x times x minus alpha 1, because alpha minus x minus alpha 1 is a factor of this. So you can multiply this, and this is actually a polynomial of degree less than this. And because p1 of x is a polynomial in E of x, implies p1 of x has a 0 in E, say alpha 2. So you can write p of x equal to p1 of x times x minus alpha 1, that is equal to p2 of x minus alpha 1 x minus alpha 2. Continuing this process, we can arrive at p of x is equal to x minus alpha 1, x minus alpha 2, x minus alpha n. Actually, comment is alpha 1 dash dash alpha n need not be different. Doesn't need to be different. It could be same. So what does that mean? If it is algebraically closed, every polynomial can be expressed as a product of linear factors. So if E is algebraically closed, every polynomial can be expressed as a product of linear factors, linear polynomials. Linear polynomials means a polynomial with degree 1. And if you take the other way, suppose p of x belongs to E of x and p of x is equal to x minus alpha 1, x minus alpha 2 dash dash x minus alpha 1 alpha n, then what does that mean? That means E is algebraically closed, because these alpha 1, see, if you are factorizing this into linear factors, all these alpha 1s, alpha 2, alpha 3, alpha n's are from E. So these are all zeros of p of x. So if it is algebraically closed, we can express as a linear factors, product of linear factors. If it is linear factors, then it is algebraically closed. So the result is a field E is algebraically closed if and only if every polynomial in E of x can be expressed as a product of linear factors, linear polynomials. Now, let E be algebraically closed and assume that there exists an algebraic extension say E prime of E, that is E prime. It's an algebraic extension, not the regular extension. E is algebraically closed, and we are assuming that there exists an algebraic extension E prime of E. Then let alpha belongs to E prime. That implies there exists a irreducible polynomial, right? And that irreducible polynomial alpha over E is nothing but x minus alpha. Because every polynomial can be, if E is algebraically closed, every polynomial can be expressed as a linear combination of products of, sorry, not linear combination, a product of linear factors. And this implies because E is algebraically closed. The reason for this one is, see, what I'm trying to say here is this is E prime and this is E, and alpha is here assumed. So there exists a polynomial P of x, and that is called irreducible polynomial of alpha over f that belongs to E of x. Then E is algebraically closed. That means P of x can be expressed as a linear as a product of linear factors. So that means x minus alpha 1, x minus alpha 2 dash dash x minus alpha n. But alpha is a 0 of P of x. So that means one of these alphas will be alpha. Alpha 1, alpha 2, alpha 3, alpha n. One of those will be alpha. So in fact, that irreducible polynomial will be x minus alpha because it cannot be a degree more than 1 because it is algebraically closed. And what does that mean? This implies alpha belongs to E. So what we are having is for every element from E is also element of E. That means E is a subset of subfield of. So that implies E is equal to E prime. So what is the result? Every algebraically closed fields do not have algebraic extensions, and that is the result. And we have one more result which we will not prove, is that every field has a algebraic closure that is algebraically closed. For example, we know that Q of X is an extension of Q, and R is also C is also an extension of Q. But for this extension, the algebraic closure is not algebraically closed. But for this extension, the algebraic closure of Q over C is algebraically closed. So we can always find an algebraic closure that is algebraically closed. What I'm saying here is Q of X, the closure of Q over Q of X is not algebraically closed. It's not algebraically closed. But here Q over C, this closure, this is a closure, is algebraically closed. So there exists an algebraic closure that is algebraically closed. That does not mean that every algebraic closure is algebraically closed. Okay. So we are coming to an end on the session on algebraic extensions with one more problem. It is actually, let E be a field of odd characteristics. What do you mean by odd characteristics, or a characteristics of n? A ring in general is of characteristics of n for some n, some integer n, if n times a. This means not multiplication, a added n times. This is actually a plus a, n times, is equal to 0 for all a in R. A ring R is of characteristics n. If there is no n like that, then the characteristics is 0. Okay. For example, if you take Z, the characteristic is 0. But for ZP, the characteristic is P. Okay. So here it is not 0, it is an odd characteristic. Meaning, so this implies there exists an odd number such that n time A is equal to 0 for all A in E. So that means 1 is different from minus 1. 1 is actually the multiplicative identity of E. It is not the real 1, because in general E can be anything. So 1 is the multiplicative identity of E. Minus 1 is its additive inverse. This is not equal to minus 1 because it is odd. Because if you take like this, 1 plus 1 is going to be 0. If 1 is equal to minus 1, then this will be 0. That means the characteristics of 1 is 2, and that is an even number. So this is not possible. So in a field of odd characteristic, 1 is not equal to minus 1. But what is 1 square? 1 times 1, that is always 1. And what is minus 1 whole square? Is also 1. So if you define a function from f to e to e by phi of a is equal to a square, then phi is a homomorphism that is not 1, 1. That implies there exists a alpha in E such that alpha is not mapped by phi. And that implies alpha is not a square of any element in E. And that implies x square minus a is irreducible, because we don't have x square minus alpha is a base number. Because you don't have a element in E whose square is alpha. That means alpha x square minus alpha belongs to E of x, which cannot be expressed as a product of linear factors or polynomials. And what does that imply? That implies E is not algebraically closed. So if there is a field that has got odd characteristic, it cannot be algebraically closed.